So in the first video, we've been over the rules of integration. So we know how to find antiderivatives for a whole lot of functions. I just want to spend a couple of minutes talking about one of the main applications of integration. So this is a very common textbook type of application for integration. We're going to use integration to find an antiderivative. So typically we might be given a derivative, in this case dy dx is equal to negative 1 over x cubed, and the problem is to find the original equation of the curve. And we've got this additional information about the curve that it passes through the point 1, negative 4, and we'll see why we need that additional information. If you've solved a problem like this before, you might want to pause the video and see how you go now that you know a few more rules for integration. Let's have a look at the first part of the solution. If we're given a derivative, we can find the original equation of the curve by integrating the derivative. So the integral of dy dx with respect to x is going to give us the equation for y. So in this case we're integrating negative 1 over x cubed. You can see here we're using a rational expression, so I'm going to have a negative factor of negative 1 at the front of the integral. We're going to use x to the power of negative 3 so that we can use our x to the n rule. N plus 1 will be negative 2. So eventually we get the indefinite integral 1 over 2x squared plus c. It's actually the c that makes this an indefinite integral. Let's have a look at the second part of this solution. So here we know that our equation is of the form 1 over 2x squared plus c. We're now going to use the additional information, the coordinates that the curve passes through, and it wouldn't matter which coordinates as long as the curve does pass through those coordinates. So we're going to substitute those coordinates into our equation. That gives us an equation where we can solve for c. So in this case, solving for c gives us a constant of negative 9 over 2. And so now, instead of an indefinite integral, we have what we call an antiderivative, the actual curve that this derivative comes from. So our curve is going to be the curve of 1 over 2x squared minus 9 over 2. We could do the same thing with the CAS calculator. It's the same question. Using the calculus menu, we could find the integral of negative 1 over x to the power of 3. And here's our 1 over 2x squared. You'll notice that the CAS calculator doesn't give us an indefinite integral. It doesn't give us the plus c part of that expression. So we could define our function as being 1 over 2x squared plus c. You can see we define the function. When we substitute the coordinates and solve for c, what we're saying is that f of 1 is equal to negative 4 because it passes through the coordinates 1, negative 4, and we would like the calculator to solve c for this equation, and there's our constant of integration, negative 9 over 2, which we could then write as our antiderivative. Let's just use this demonstration on Desmos to talk about the difference between the indefinite integral and an antiderivative. So it's the same problem that we've just worked through together. So our yellow dotted line on the screen at the moment is our derivative, our dy dx. Our first step was to use integration to find the indefinite integral. And so we get the curve 1 over 2x squared plus c. And we can see how that relates to the derivative. On the left-hand side of the y-axis, our derivative is above the x-axis, it's positive. And we can see for this region of the graph, the curve is increasing. On the right-hand side of the function, we can see our derivative is a negative value, it's below the x-axis, and so our original function is decreasing for that region of the graph. I've added a slider in for the constant integration c. At the moment it's 0, so as we look at different values of c, we can see that we're really talking about exactly the same curve. It's just got a vertical translation about it. So this is the point of the indefinite integral. All of these curves, no matter where this value of c stops, all of those are going to give us exactly the same derivative, negative 1 over x cubed. One of those indefinite integrals, or the indefinite integral at some point, is going to pass through our coordinates here, 1, negative 4. That was the additional information in that question. So we can see now, as I slide the value of c around and try to stop right where the curve passes through that point, we can see that it stops when c is negative 4.5, in other words where c is negative 9 over 2. So we had a look there at the difference between, let's just go back, and at the difference between an expression like this, which is an indefinite integral, and a particular value of c that gives us the antiderivative for a derivative. So in both of these videos, parts 1 and 2, just to recap, we use many rules to find integrals of polynomials, but also the other functions as well. You might remember that we also saw some additional rules that are not typically written on the formula sheet, where we can take k out of the front of an integral, where we have f of ax plus b, for example. And much of the time when we were finding integrals, it was important to be aware of the index laws that we use fairly regularly in this course. The second part of the video, we had a look at applying indefinite integrals to find an antiderivative, and we've had a bit of a discussion about when do we use those terms, indefinite integral and antiderivative. So now that you've taken some notes, you probably have some questions that you'd bring to class. Write those questions down. If you can complete the Google form, log your attendance and check your understanding. And that completes this lesson. Thank you.